Hello, hello. Okay, let's try this. I'm gonna try to record these. Well, if it doesn't work, it doesn't work. Last time we looked at examples of cross-product construction, so I quickly want to do a notational review. Otherwise, this is gonna get very confusing very quickly. Actually, let's do this first. Did you guys learn about NFAs? Yes, okay, great. So NFA versus DFA. So the way you can think about this simply is, let's say I have the state A, I have a 0, I have a 1, and this is my accepting state. So really quickly, what is the language accepted by this DFA? What is it? I read a 0, and then I can read as many 1s as I want, or 0 1s. Give me a regular expression for the language accepted by this DFA. Great, 0 1 star. You can be confident. You don't need to be shy. You can be confidently wrong too. Okay, 0 plus 1 star. Great. Now, with the DFA, for a given start state, on reading input 0, I can only go to one state. However, for an NFA, there's two differences. So, one of the differences is in an NFA is after reading the same character, I can go to multiple different states. So for example, on reading 0, I could go here, or on reading 0, I could go here. So there's a few caveats here with NFAs. So what's the language accepted by this NFA? It's still 0 1 star. So that's right. So there's non-determinism here. If I take in the string 0 1, let's just say, right? Let's say, for whatever reason, I'm at the start state and I choose to read in a 0. I can go here if I want. But if I go here, there's no transition defined after reading the 1, correct? So I've read my 0 string. If I try to read a 1, I can't go anywhere. So if we go through this path of execution, on the left-hand side, I won't be able to accept the string. So my point, if I take the string 0 1 and go through this path of execution, there's no accepting path on the left-hand side. So if you only test this path, you would think you might reject the string. However, if I take the same 0 1 path, 0 1, I end up in an accepting state here. So we define NFA string acceptance differently than DFA string acceptance. An NFA accepts a string if, when you try all possible execution paths of the strings on the machine, so I could go here, 0 1, or 0 1, if at least one of the paths leads to an accepting state, then we say that the NFA accepts the string. So as I said, in an NFA, for a given state, on a specified input character, you can transition to multiple states or no state. If any one of the possible executions of the string on the machine leads to an accepting state, we say that the NFA accepts the string. Otherwise, we say it rejects the string. So that's some background that's important here. So one concept was multiple transitions. Another concept was one of the many execution paths. Another thing that an NFA has is an epsilon transition. So if I add an epsilon transition here, what that means, now let's do a different thing. Okay, so I have my start state, I read the string 1, I have state A, I accept. Or I take an epsilon transition here to my state B, and if I read a 0, I stay in this accepting state. So what is the accepting language here? If I go through this path, if I read a 1, I end up in an accepting state. But after I read a 1, there's no transition defined. So I can't say it's 1 star because there's no self loop here. Let's take a look at this. So epsilon is just the empty string. So at any point in time, I can non-deterministically move here. And then no matter how many zeros I read, I'll stay here. So this portion can be captured by the expression 0 star. So this is the language accepted by the NFA. So again, to drive home the point, this epsilon transition means at any point in the string, I can non-deterministically move here. Let's actually make a change so that we can actually understand how you can leverage this. Let's say I put a self loop of 1 here. Now, let's say I read the string 1, 0, okay? I want to read in the string 1, 0. Option number 1 is I go here, I read in a 1, and there's no 0 transition defined out of here, right? There's no 0 transition. So if I try to go here, I'll reject the string, so that doesn't work. I can decide, hey, I'm going to make a guess to take this path non-deterministically. And then I read my 0. So I've read my 1. To make this clear. So my string is 1, 0. I've decided I'm going to read my first 1 here. I'm going to make a guess for free that I can move here without consuming any more input characters. Then I read my 0, and I've accepted the string. So this is one possible execution path on the machine. Let's look at just one more case. I have the epsilon transition at my disposal. So let's say I'm, again, concerned about the string 0, 1. If I can use my epsilon transition immediately and end up here if I wanted. So I use my epsilon transition. I keep the fact that I'm in a 0 state. But after I consume my 0, there's no 1 to be consumed here. So I can't go anywhere and I reject the string. So I just showed you for the same string, there are multiple possible execution paths on a machine. I just want to drive home the point that in an NFA, you do not need every single execution path on the machine to accept. You just need one of the many to accept. Is that clear? Okay. So that's concept 1, understanding the differences between NFAs and DFAs. The second thing is states themselves can be tuples. So in this machine I made here, I made my start state S comma A. I made my start state S. In both NFAs and DFAs, what I'm allowed to do is I can actually make these states tuples if I wanted. So S comma, let's just some random thing 1. We'll put a 0 here, and we'll make this A comma for whatever reason, if I wanted to do this, I'm allowed to do it. So what is the transition function for this machine? The transition function on the left-hand side, let's say these are both NFAs. On the left machine, after I read 0, where do I go? Hey, great. If I tell you this is an NFA, do I write the letter, after reading 0, if I tell you this is an NFA, you have two options. Do I say A or do I say the set containing A? Why? Why the set? Right, because the NFA can have multiple states. So that's important. If this was a DFA, you wouldn't write the set. So let's call that. Okay. Similarly, let's do the same thing on the right-hand side. I'm now in state S1. So this is my state. This will become important later. I read in an input character 0. And where do I end up? What do I put in the set? The tuple a comma 2. So the only reason I did this was to demonstrate that there is nothing wrong with making the name of the state a tuple with 2 elements, a tuple with 3 elements, a tuple with 4 elements. As long as these are unique, you're fine. So I can name it by a character. I can name it by a tuple. These machines are exactly the same in terms of the strings that they accept. If I circle the accepting string. Is that clear? Yeah. You can do the same thing with the DFA. The reason I chose NFA here, so yes, but yes, you can name the states of a DFA to be tuples. The reason I said NFA here is I wanted to use the set notation because later we'll see that we're going to transition to multiple states. So one last thing, if I put a 1 here and I write B here, or if I put a 0 here and I write B here, now I add, after reading 0, I can go to state A or B. So I have 2 states. And over here, if I add another state on reading 0, let's call this C comma 3. Okay, so after reading 0, I could go either here or I could go here. So what do I need to add to the set? Just the tuple C comma 3. Does that make sense to everybody? Okay. Let's move on. Let's take this problem. So now, this question says, let L be an arbitrary regular language over the alphabet sigma. So L is some regular language. So what does this mean? If L is a regular language, that means we know that there is a DFA or an NFA that accepts the language L. Agreed? Okay, so there's either a regular expression or a DFA or an NFA that accepts L. But remember that regular languages and the language is expressible by regular expressions, and the language is expressible by DFAs, and the language is expressible by NFAs are all one and the same. They're all regular languages. So because they haven't told me anything about L, I'm just going to assume that L has a DFA. So L is regular, L has a DFA. So L is not, prove that the following languages are also regular. Flip odds L is this function is equal to flip odds W such that W belongs to L, where the function flip odds inverts every odd index bit in W. For example, applying flip odds on this string will, this is too long, okay. So 0, 1, 1, 0, 1. This function, flip odds, accepts a string and returns the corresponding string where all of the odd index bits are flipped. So if we start 0 indexing, this is my index, 0, 1, 2, 3, 4. This is an odd index, so I flip it. This is an odd index, so I flip it. So the output of this is going to be 0, 0, 1, 1, 1. Did I do that right? It says 1 index? Okay, fine. We'll use 1 index. 0, 1, 0, 0, 1, let's say. So 1, 3, 5. This becomes 1, 1, 0. Then I put a 1 in between and a 0. Is that right? Okay, great. So the way that you can understand this set, flip odds L is the set obtained by enumerating all of the strings W in language L. So language L, remember they gave us as a regular language. We enumerate all of the strings in language L for every single W in language L. We get that string. Then we apply the flip odds operator onto that string W and get the result of that function and put all of those results into one large set. So again, L is a regular language. L has an possibly infinite number of strings in it. We take every single string in the language L. We apply the flip odds operation onto that string. So we flip all of the odd index bits. We take the resulting string, we put it into a set, and we call it flip odds L. Does that make sense? Okay. So now I want to prove that the language flip odds L is regular. So I want to prove that flip odds L is regular. Okay. So one way I like to think about this is we already said over here on the right-hand side, L is a regular language, so L has a DFA. So assume that we have a table over here, and this table has a magical box on it. And this magical box is the DFA for L. Okay, so this is the DFA for L. Let's, what is it? A DFA is a 5 tuple that contains, all right, so this is the DFA for L. I don't know how it's built. I don't know the states of L. The problem doesn't tell me anything about L except it's regular, so I have some arbitrary DFA and some set notation. I do not know the states. I do not know the transition function. I do not know the exact accept state. All I know is that they exist and they're defined. Now, what I want to do is enumerate every possible string in this language. So let's take a random string, 0, 1, 1, 0. And they said that we're 1 indexed, so this is index 1. So I take a specific W. W is a string in the language L. And I'm standing over here. And what I want to do is I want to pull the first character from the string, look at it, and say, hey, if this is an odd indexed character, flip it, and then pass it into the black box on the desk. So this guy takes this. He asks, is it odd? Flips it. So he pulls this thing out. And then passes it into the machine on the desk. Then we move on to the second bit. So we've consumed the first character. We move on to the second bit. So is it odd? No, because the index is 2. So we don't flip this bit. We keep the bit the same, and then we pass it into the machine on the desk. And so on and so forth until we consume the rest of the string. So this DFA accepts the string. If this DFA accepts the string, the light on top of the DFA lights up. And we know that we've accepted the string. So again, L is a regular language. We're symbolizing L by this DFA that's on the desk. We're saying, hey, we're going to feed a sequence of characters into this black box. If it lights up, the DFA for L accepts the string. If it does not light up, the DFA does not accept the string. I'm trying to prove that the language flip odds of L is regular. So I'm going to take a string. I'm going to flip all of the odd. I'm going to take the string from left to right. I'm going to flip the odd index bits, pass it into the black box on the desk, and I'm going to do that character by character. If the black box on the desk accepts the string by the time I'm done with this operation, then I know that I've accepted the string. If it does not, then I reject the string. Does anyone have questions about this conceptually? Raise your hand and ask. Or if you're totally lost, that's fine. Yeah.
What is the rejection?
The light doesn't light up.
No, but like what would an example be?
So we know that the language L is regular, right? So if we take a string and we flip all of the odd bits, and the DFA for L does not accept that string, that's a rejected string. So we have a string, we flip all of the odd bits, we pass that new string into the DFA for L. If that rejects the string, then we reject. Does that make sense? Any other questions conceptually? Thumbs up, thumbs down. Like, this is really confusing for a lot of people, so just let me know. Good? Okay. Not good. That's okay. One more time then. Sorry if you already get it. We have a language W. We have a language L. We have strings in this language L. We know that L is regular. We're trying to prove that the language obtained by taking every string in L and flipping all of the odd bits, the language we obtain by doing that operation is also regular. In order to do that, we leverage the fact that L is a regular language. Therefore, there is a DFA for L. We don't know how it works or how it's built, but we know it exists with some arbitrary states and transition functions. In order to prove that the new language is regular, we build an NFA that passes characters into the black box DFA. And if the black box DFA accepts the string, then our new NFA that we're making right now accepts the string. Otherwise, we reject the string. So this whole thing is an NFA. So we're going to build this NFA. So we're going to call the NFA M prime, which is a 5 tuple containing Q prime, S prime, delta prime, A prime. Sigma is the same. So this is our new NFA. And then we have our old DFA as a black box. M is this DFA on the desk over here. This is M. Q, S, delta, A, sigma. This is a black box. And this is what we are trying to build. So let's build the NFA M prime. So Q prime, S prime, delta prime, A prime, and then sigma is the same. Okay. Let's start here. The states of the new NFA that I'm building need to keep track of whether I'm reading an even or odd index bit. The first bit that I read is an odd index bit. It's 1, right? 1 is odd. So I said before that states of DFAs can either be strings or tuples. How can I build an NFA that keeps track of whether the character that I'm reading is even or odd? Yeah. Yeah, okay, one of the tuple things can be the index, right? Then I know that if the index is even, I'm on an even index. If I'm on an odd index, I know it's odd. So there's an issue with this. That DFA, if I keep track of every index, the DFA that I build is dependent on the size of the string, right? So I can't do that. What's right? Just have it say like true or false. Yeah, we can have it say true or false, and then we can keep alternating between the states. So visually, you can think about this as, let's just say is even or is odd. We have some starting state S1 or S true. And then we have some state F false. Don't worry too much about the first one. And then every time we read a character, we jump between these two. So I need to take the states of my old machine that I have, and then I need to add on an even or odd indicator to see in the new machine that I'm building, whether I'm in an even or odd state. So essentially, if my old states were Q1, Q2, Qn, my new states are Q1, comma, let's just say true, Q1, comma, false, Q2, comma, true, Q2, comma, false, and so on and so forth. So how can I represent this operation in set notation? Yeah. Yes, I can take a Cartesian product with a set of true and false. So I take the states of my old DFA black box, and then I take a Cartesian product with true or false. I'm actually just going to call it even or odd. Even or odd. Okay, so I take a Cartesian product, and then this gives me, for every state that was in the black box DFA that I have, I take that state representation and I add a flag on even or odd at the end. So the first character that I read, starting over here, is it even or odd indexed? It's odd indexed, right? So what I can do is I can take the start state of the old machine and start from the start state of the old machine with the caveat that I add the flag that I'm in the odd position. So this S is the start state of my old DFA, and I'm going to add the odd flag here. Okay. Let's switch this around. So let's say this NFA, I'm passing strings in, I'm going from left to right, I'm going from left to right, and the box on the desk blows up. So this is like, okay. Does it matter whether my string was even or odd length when that goes up? No, it doesn't matter at all. I can have an even length string that's accepted by this, and I can have an odd length string. So I'm going to have two accepting states, or two sets of accepting states. One set of accepting states is all of the times the black box DFA accepted the string, and the string length was even. That's option one. Option number two is all of the times this black box accepts the string, but the string length is odd. So how can I express that using set notation? Yeah. Yeah, I can take all of the accepting states of my old machine, and then I can take the product with even or odd. Now the tough part, the transition function. So let's say I read in the first character. Let's say I read in, I'm gonna get rid of some of these. So at first I read in a character 0, it's odd. If I read in an odd character, so the first character that I read, let's just say it's 0 and I'm in the odd state. This, I'll just show that this is odd. Probably should have not used that, but that's fine. This O is odd. It should be a square. Fine. This is odd. So I read in a 0. The first state that I'm in is I read in a 0 and it's odd. What do I need to do to the 0 before I pass it in? It needs to be flipped, right? So I'm going to flip my 0 into a 1. And then I'm going to be in an even state, right? I'm going to now flip into an even state. So this is a general idea. Instead, what we're going to do is I'm in some state. So yeah, that's how this would work in this case. So now let's say my NFA that I'm building, delta prime. Remember, the set of states for my NFA are tuples. So I'm in some arbitrary state Q, and I'm in the odd state, and I read in an input character C. So my state is a tuple. I read in an arbitrary input character C, and I'm in an odd state. The first thing I need to do, as we said, is flip whatever character I read in, I need to flip it. So if C was 0, C needs to become 1. If C was 1, C needs to become 0. So how do I determine what state to move in this machine? This machine's transition function is given by just delta. So if I take delta and read in C, that's going to take me to the next state of this machine. But I flipped the bit to make it odd. So instead, I want to take delta and I want to make it C complement. So the first state of this machine is going to be delta of Q, comma, C complement. This is the state of my old machine. Okay. Now, I need to change my flag indicator from odd to even, because the next character that I read is going to be even. And this is also a tuple, by the way. So does anyone have any confusion about this transition function? Does anyone understand the transition function? Yeah, you kind of get it? Okay, good. Does anyone want me to go over it again? Okay, sure. Yeah. Yeah, what's your question?
Why have a tuple in a set? Why not just stop the tuple?
We'll get there. Okay. So, why have a tuple in a set? That's a good question. But let's explain the transition function again. In my old machine, I'm building a new NFA. The states of the new NFA that I'm building are tuples. So one possible tuple is Q, comma, let's just say even. So this is the state of the NFA that I'm in. We can draw that pictorially as this is the state, Q, comma, even. Okay, I read in an input character C. And I move to some state. The first state of this tuple is dependent solely on the old DFA. So this Q represents the state in the old DFA. Good so far? So in the old DFA, so this is, let's just call this the old DFA. It's abstract. I know I'm in some state Q. And I read in an input character C. What state am I going to now? Delta of Q comma C, right? Does that make sense? Whoever else? Yeah, okay. So in the same way, if I'm in an even state, the first element of the tuple of my new state is going to be given by the state of the old DFA after reading C. So again, this is my new NFA. The first element of the tuple that represents the state of the machine is given by the old DFA. Well, if the old DFA is reading C as an input character, it's going to go into delta of Q comma C. So therefore, the first element of this tuple is delta of Q comma C. But it's a tuple and we have a second element. if my previous bit was even, my next bit is going to be odd. Does that make sense? Did whoever asked that? Okay. So this was for the odd case, right? What we can do is we can do the same thing. So this was for the odd case. If I'm in the even case, what's going to happen? Well, I'm defining my new transition function. Exactly as I said over there, I'm in some arbitrary state q comma e. I read in an input character C. Since this is an even bit, I don't need to flip the character before passing it into the NFA. So the state that my old DFA was in, the one on the bottom, is delta of Q comma C. And the next bit that I read is going to be odd. And I put that into a tuple, and I put that tuple into a set. So does anyone have any questions about the transition function or need me to go over it again? I know it can be confusing. Ask, yeah. For which one? I only want to flip odd bits, right? So if I'm standing over here and the index I see is even, I just want to pass it. If it's odd, I want to flip it. Any other questions? I'll come back to that set question. But before that, does anyone have questions about the transition function? No? Good? Okay. So he said, why are we using a set? And he's right, we don't need a set. So let's say I remove all of these set notation brackets. What have I just built? I built a DFA, right? An NFA is the same thing as a DFA, except for an NFA, if you have a DFA, you can turn it into an NFA by just adding brackets to all of the sets. If you have an NFA where the transition function leads to only one other state, you can just remove the brackets and it becomes a DFA. So in this problem, zooming back out a bit, we said we're trying to prove that this language is regular. In order to prove that this language is regular, we can either build a DFA or an NFA. The reason I chose an NFA is because it's more flexible. In the case that I needed multiple transitions and wanted to go to multiple states, I could have done that. So I chose an NFA originally because I didn't know what the transformation was going to be. But now I see that they all lead to one state and I can remove them. It wouldn't be wrong if you left it as an NFA. This thing we assume to have a DFA for. To prove that this is regular, we use the DFA for this as a black box. Because we can build an NFA that accepts flip odds of L, that uses this as a black box, flip odds of L is regular. It's a bit convoluted, but at a high level, does that make sense? Okay, I wonder where questions like this are going to show up. It's almost guaranteed that you will see something like a language transformation question on midterm. Like they always put one of them on there. So by they, I mean we. So, yeah, practice. I went through this slowly because I wanted you guys to understand the process. Once you do one or two of them, they'll start to flow and you have some practice in your homework too. I'm going to leave it at that for today unless there are any other questions. Yeah. Yeah. So it's like, if this were like questions, it's suffice to say, like, if flip, then no, you don't even need this. Okay. I just wrote that as notes. Because clearly, like in this state, right? If I wanted to be really pedantic and complete, you know what I would write is, I would say that Q belongs to the set of states Q from my old DFA. C is a character in the alphabet sigma. If you really wanted to do that, you can. Okay. So yeah, we know what they are. Especially if you define here clearly that this is the NFA and this is the DFA. So I'll pose this as a, does anyone have any more questions about language transformation? Yeah. Why did I create a DFA and DFA? Okay. So we'll start here. I know that L is a regular language, correct? Whoever asked that, you did, right? Yeah, or did you ask? Who asked the question? Yeah, okay. We know that L is a regular language, right? So L has a regular expression. L has a DFA and L has an NFA, right? The language is accepted by regular expressions, DFAs, NFAs, all the same. So I'm going to leverage the fact that L has a DFA. I don't know what the DFA is. It doesn't matter how it's defined. All I know is that it exists, and it has some arbitrary states and some arbitrary transition functions. My goal is to prove that this language is regular over here. So I'm going to build an NFA for this language. Flip odds out. Because if I build an NFA for this, that means that this language is regular. So in the term language transformation, I'm transforming this language into the language accepted by this DFA. So I'm building a new machine that essentially the goal of this machine is to transform my input string and pass it into this DFA. So if this language is regular, then this language is also regular. It's as simple as that. If this language is not regular, then we can't say anything about this language. If this language is regular, then this one also has to. Any other questions? So yeah, when you see something like this on the exam, always